In this pre-calculus algebra video, we will use a matrix to solve a linear system of equations. We have already solved systems of linear equations with three unknowns using elimination. Some students will find using matrices an even easier way to keep track of the writing. I'm going to encourage you to take very careful notes during this video and jot down the plan of what we're doing, not just follow along and copy the example, but follow along, copy the example, and write your own notes of what we're doing when and why. Here's the first step, is to be able to translate a matrix translate a system into a matrix. Here's how it works. This is a matrix. It's an ordered array of numbers. We're going to put two brackets and this augmented matrix. What we're going to do is go into the system of equations, and we're going to pull out just the coefficients. So the 5, -2, -3, and then the constants 0. When I do that, it's going to look like this. I'd have 5, let me change the color there so it shows up a little better. 5, -2, -3, and then the constant 0. When I look at the x, y, and then there's an absence of a z, notice that that's a 0 z. So the coefficients I'll write are 1, 1, 0, and then the constant is 5. For the last row, notice that there's an absence of y's, so the coefficient is 0, 2, 0, -3, 4. And then I'm going to draw a vertical line here in the matrix to separate the constants from those coefficients, and that's what we'd call an augmented matrix for the system. Practice that, make sure you can do that. Now, here's the last step. I'm going to always encourage you, and you'll see why at some point, if you're not doing this, you'll understand why you wanted to have done this. We're going to be doing some pretty long problems, and it's the type of problem that if you make a mistake in the first step, so this easy step of just translating the numbers over into the ordered array, into the matrix, if you make a mistake there, then the entire set of work that you do, every step, is incorrect. So you want to stop and double check that we've got this right. We've got 5, -2, -3, 0, 1, 1, 0, 5, 2, 0, -3, 4, or go down in rows, 5, 1, 2, -2, 1, 0, -3, 0, -3, 0, 5, 4. So check it every which way. And also check to make sure that your variables are in order. Notice that this was set up with all the x's, then the y's, then the z's, and it was all solved for a constant. So that's how we can be certain that we're not making some critical error that's going to send us into a big problem. The next step to using matrices to solve a system of linear equations is to be able to perform row operations. Now there are two operations that are allowed. Number one, we can multiply a row by a factor, by a scalar factor, so by a number, positive or negative fraction. So we could multiply row 1 times 1/2. I know it looks like we're dividing, but we're going to call it multiplying. The other row operation that's allowed is you can add 2 rows. You can add 2 rows. Those are the two things that we're allowed to do. Isn't that nice that it's so concise and small? There's only 2 things that we have to be concerned with, either multiplying by a factor or adding 2 rows. Those are the only 2 things we're going to do. So let's look and see how you would go about doing this. Like, how do you multiply a row? We're going to use this notation, 1/2 r sub 1, to mean take the row 1 and multiply it by 1/2. So in other words, we're going to take 1/2 and distribute it to the 2, negative 6, 4, and 10. And it might look like this: 1/2 times 2, 1/2 times negative 6, 1/2 times 4, 1/2 times 10. 1/2 of 2 is 1. 1/2 of negative 6 is negative 3. 1/2 of 4 is 2. And 1/2 of 10 is 5. Now, another way to see this would look like this. If I wanted to do 1/2 row 1, and now this is going to be the new row 1, but if I were to go back to my original row 1, here's one other way to show it. I could write my row 1, 2, negative 6, negative 4, 10, and to multiply by 1/2, I could just show it divided by 2. What I'm doing is multiplying by 1/2, but I can show it as dividing by the denominator. So 2 divided by 2 is 1, negative 6 divided by 2 is negative 3, negative 4 divided by positive 2 is negative 2, 10 divided by 2 is, oh, and look, this was a positive, wasn't it? Ignore that for just a minute. Sorry about that error. It was 2, negative 6, positive 4, positive 10, right? So 4 divided by 2 is 2, and then the last one, 10 divided by 2 is 5. So you could do that either way. You could write it as a factor in front because we're distributing, or you could show the distributing by showing it over that factor. But that's how we could multiply a factor. When you've done this, what we'll do is now rewrite the matrix to show that new row. And when we rewrite the matrix, the only one that's changed is row 1. So row 1 has now become 1, negative 3, 2, 5. Row 2 and row 3 have been unchanged. So we just copy them over. So here's the result. Let's look at another example. What if we wanted, looks like the screen is just off the window. There, I think that shows it now. Perform the row operation and write the new matrix. We're going to do negative 3 times row 1 and then add that to row 2. Here's how I'm going to show it. Negative 3 times row 1 is negative 3 times 1, negative 3, 2, and 0. So what that negative 3 times row 1 would look like is negative 3, positive 9, negative 6, and 0. I'm going to double check before I go on. Negative 3, positive 9, negative 6, 0. And then I'm going to add that to row 2. When I add this new row 1 to the row 2, I get negative 3 plus 3 is 0, 9 plus 1 is 10, negative 6 plus negative 1 is negative 7, and 0 plus 7 is 7. So I've got the new matrix. Row 1 is unchanged. I know we multiplied it by negative 3 to use it, but we haven't changed row 1. We were just using this row 1 times the negative 3, but we haven't actually changed row 3. Notice in this instruction of what we were doing that we were taking negative 3 times row 1 and adding it to row 2. So what that alerts me to is that row 2 is the only row that's actually going to change. So 1, negative 3, 2, and 0 remain the same. 2, negative 2, 1, 3 remain the same in the row 3. But my new row 2 is going to be 0, 10, negative 7, and 7. And that's the answer to this question. Perform the row operation and write the new matrix. This is what it would look like. Next, we're going to draw these different things together. The act of writing out a matrix and then performing row operations. To do what we would call elimination and solve system of equations. Now, I've written the augmented matrix here to the left. Double check that if you need to. Pause the video to make sure you can see how I wrote the augmented matrix, and double check it that you agree that it's written correctly. But next, here's, some students find this very easy, others find it very difficult. Here's what I've learned about helping students perform these row operations and use that to solve a system. What you need more than anything is to understand the plan, the goal. Don't wander aimlessly in this maze and get lost. Have a plan. Don't just do one thing after the other, taking a step at a time, going off, wandering in the wilderness. Where there is no vision, the people perish. That's an ancient proverb I've come across and used often. And here's how you do that. You have this goal in mind. Here's the goal. We want ones across the diagonal, and we want zeros below each one. So we're going to shoot for getting a 1 in this first spot, and then get zeros below it. Get the 1 in the second spot for row 2, and get a 0 below it. And then get a 1 in the third spot, and there's no zeros to worry about. All these blue smudges are the numbers that we're left with. So our goal is to get a 1 and then zeros, 1 and a 0, and then a 1. And that's it. Here's the plan. You do this, you accomplish this goal by getting the 1 first. And then what we're going to do is we're going to bounce off of that 1 to get these zeros. Are you ready to try this? How fortunate for us that we've already got the first 1 handed to us. So the first step, if this first number up here wasn't a 1, we would have done some row operations to make it a 1. Now here's one other trick. We said that the row operations were that you could multiply by a scalar, so multiply by a number. And we said you could add rows. Here's a third thing you can do. You can just exchange rows. You can move rows around from, so if the 1 was down here and this was a -1, we could just exchange, swap places for row 1 and row 3. But we want to start by getting a 1 here in this spot. And fortunately for this one, we don't have to worry about doing that because the 1 is already there. Once we have that 1, once we already have that 1, we're going to bounce off of the 1 to get ones, or rather zeros, below it. So the plan is get the 1 and then bounce off of the 1 to get zeros. Here's how we'll do that. We're going to take row 1 and multiply it by -2. Why -2? Well, when you look at this 2, we want that 2 to be a 0. We're thinking, what could I add to a 2 to get 0? What would I need to add to 2 to turn it into a 0? Well, if you're saying, well, obviously that's a -2, then you're on the right track. So what we want is a -2 to add our 2 so that we can get a 0. So that's what we're going to do. We're not going to change row 1. We're going to keep row 1, 1, 1, -1, -2, but we're just going to use it. We're going to bounce off of it to get this 0. So -2 times row 1, -2, -2, +2, +4. Row 2 is 2, -1, 1, 5. And when I add those rows, I get a 0, -3, 3, and 9. I'm going to stop and double check. 4 plus 5 is 9, 2 plus 1 is 3, -2, -1, -3, -2, 2. Here's our coveted 0. That's what we were going for, right? So it looks good to me. I'm going to go ahead and write those numbers in my new matrix. That's my new row 2. And now we want a 0 where this -1 sits. We want a 0 in this first column, row 3. So to get that 0, I'm simply going to add row 1 and row 2, because a 1, if I'm thinking, okay, what do I need to add to -1 to turn it into a 0? The answer is a 1, right? So if I want to add a 1 here, I already have the 1. It's already a 1. I don't have to multiply it by any factor. I already have the 1. So I'm going to bounce off of that to get my new row 3. So row 1 is 1, 1, -1, -2. Row 3, -1, 2, 2, 1. When I add those together, I get 0, 3, 1, -1. Don't take a shortcut here. Check your work. Use a calculator if you are prone to arithmetic errors, and just put that addition in there with those negatives. Don't let that throw you off. -2 plus 1 is -1. -1 plus 2 is 1. 1 plus 2 is 3. And 1 plus -1 is 0. So it looks like my new row 3 is 0, 3, 1, -1. Well, I've gotten my first column done. We have a 1, 0, 0. Now we're going to move on to column 2. What's the plan? To get a 1 and then bounce off of it to get zeros below it. Why are we doing that? Because here's our goal. We want it to look like this, where we have 1s in the diagonal and zeros below each one. So if we want 1s in the diagonal, we need this -3 to stop being a -3 and to be a 1. Here's how we do that. Here's how we get that 1. We could multiply row 2 by -3. Here's what that would look like. Our row 2 is 0, -3, 3, 9. And if I multiply by -1/3, it's the same thing as dividing by -3 all the way across. So when I do that, 0 divided by -3 is 0. -3 divided by -3 is 1. 3 divided by -3 is -1. 9 divided by -3 is -3. So now our new row 2, our row 1 hasn't changed. Our row 3 hasn't changed. But our new row 2 is going to be 0, 1, -1, -3. We're one step closer to our goal of getting our matrix to look like this. Next, we want to get a 0. We got the 1, so now we want to get a 0. We want a 0 right here. We want the 0 right here, right? I've just copied the matrix over from the left to the right. But we want this 3 to be a 0. We can make this 3 0 by bouncing off of the 1 above it and then adding it to the 3. Because what I'm thinking of is, what could I add to 3 to get a 0? I could add a -3. How do I get a -3? I bounce off of the 1. I make the 1 allow itself to be multiplied by a -3, and then I'm going to add that to my row 3. Here's what it would look like. We'd have -3 times row 2 is 0, -3, +3, +9. Row 3 is 0, 3, 1, -1. Just copy those over. And now I'm going to add 0, -3 plus 3 is 0, 3 and 1 is 4, 9 and -1 is 8. So I can put that down here as my new row 3. My new row 3 is 0, 0, 4, 8. We are so close to finished. We took care of column 1. We have a 1 in the diagonal, 0 is below it. We took care of column 2. We have a 1 in the diagonal, 0 below it. Now we just need this 4. We need this 4 to be a 1. What could we multiply 4 times to turn it into a 1? If you're saying 1/4, you're correct. If I multiply 1/4 times 4 and then multiply the 8 times 1/4, because you have to do it to the whole row. I'm ignoring these zeros because 1/4 of 0 is still just 0. But here's what it would look like. We would take 1/4 of this, so it's the same thing as dividing by 4, right? So our new row 3 would be 0, 0, 1, 2. And I'm going to write that in the matrix, and we're done. 0, 0, 1, 2. Our matrix is now finished. But the problem hasn't been asked, because it said, the question was asking us to use the matrices to solve. So we did it, we met the goal. But now, to solve for x, y, and z, we're going to transfer this matrix back to a system. So this would be 1x plus 1y minus 1z equals -2. 1y minus 1z equals -3. And z equals 2. I'm going to use back substitution. And when z is 2, I can substitute that 2 in for z to find y. And then I can use back substitution to find x. Here's what that would look like. I start by applying, by using that this z is equal to 2. And I'm going to go to the y minus z equals this row right here, this equation 2, y minus z equals -3. And in place of z, I can fill in a 2. So I have y minus 2 is -3 by adding 2 to both sides. I could find that y equals -1. So now I know that z is 2, y is -1. So when I go to equation 1, x plus y minus z would be x plus -1 minus 2, and that has to equal 2, so I can solve for x. So we have x minus 1 minus 2 would be -3 equals -2. Add 3 to both sides to get that x equals 1. And there we have it. We've got our solution now. And we could write this as an ordered pair 1, -1, 2. We could write this as the ordered pair. X is 1, y is -1, z is 2. And that is our final solution, our final answer. We have solved the system of equations. Now, there is one more way to do this. Once we get this far, if we get 3 more zeros, if we were to get 3 more zeros, then our x, y, and z would just sit in this last column. So if we went a little bit further and made these zeros, so our new goal would become 1's in the diagonal, 0 everywhere else except for the 3 constants at the end. If we did that, this is called Gauss-Jordan elimination. If we do that, we're going to have an end result matrix that gives us the whole solution right there. So if I wanted a 0 here in the top row, column 2, I could multiply -1 times row 2 and add that to row 1 to get 1, 0, 0, 1. So that's my new row 1. Next, I could go for the 0. So notice, by the way, I've got the first column, second column. Now I need a 0 where this -1 is. I could accomplish that by adding row 3 to row 2. So 1 plus -1 would be 0. Row 3 is 0, 0, 1, 2. Row 2, 0, 1, -1, 3. Adding them, we get a 0, 1, 0, -1. Right here, 0, 1, 0, -1. And look what we have now. we've met our goal where we have ones in the diagonal, everything else is 0. And here, our x, y, and z just sit. So x would equal 1, y is negative 1, z is 2. Notice it's the same result we got last when we used the back substitution, right? This is the same answer. I just wanted to show you that you could also continue reducing this matrix so that you had all zeros, and then you wouldn't need to use that back substitution. Well, I hope that this video has helped you with this process of using matrices to solve systems of linear equations. Please let me know if you have any questions about the examples that we worked, and keep practicing. That's the best way to get good at this.